Right now, underneath the surface of the Pacific Ocean, there is a mass of water the size of a continent sitting at temperatures 5 to 6 degrees Celsius above normal. It has been building for months. It is moving east, and the scientists who track it for a living are not using words like concerning or worth monitoring. They are using words like unprecedented and we have never seen this before. The last time something like this happened was 1997. That event killed an estimated 23,000 people, displaced tens of millions more, triggered the most severe coral bleaching ever recorded, destroyed the fishing economies of entire countries, and contributed to what was then the hottest year in recorded history. What is forming right now in the Pacific could be bigger. And here is the part that should genuinely disturb you. The 1997 event took everyone by surprise. Scientists did not understand the mechanism well enough to predict it with confidence. They watched it develop and reacted after the damage had already begun. We understand the mechanism now. We've been watching this one build for months. We have the data. And despite all that, scientists are still scared. By the end of this, you are going to understand something that almost no coverage of El Niño actually explains. Not what El Niño does. Most people have heard that. But why this particular one is different. What is physically sitting underneath the Pacific right now? How large it is? What happens if it reaches the surface? And why the number that climate scientists are watching most closely has already crossed a threshold that, historically, precedes the worst outcomes. The Pacific Ocean covers more than 30% of the Earth's surface. It is larger than all of the land on the planet combined. And under normal conditions, it operates like a machine. Trade winds, steady winds that blow east to west near the equator, push the warm surface water of the Pacific from South America toward Australia and Indonesia. That warm water piles up in the western Pacific. Meanwhile, on the other side, near Peru and Ecuador, that movement of warm water away from South America pulls cold water up from the deep ocean. This is called upwelling. That cold water coming up from depth is not just cold. It is rich in nutrients, phosphates, nitrates, the chemical building blocks that feed the microscopic organisms at the bottom of the food chain. That upwelling is why the waters off Peru support some of the most productive fishing in the world. Billions of anchovies, millions of seabirds, entire economies built on what that cold water brings to the surface. Now here is what El Niño is. It is when that machine breaks, the trade winds weaken, the warm water that was piling up in the west stops being pushed there and starts moving back east. A massive wave of warm water, not a breaking wave, a slow thermal wave hundreds of meters deep, begins traveling across the Pacific toward South America. It takes months to cross, and when it arrives, it sits on top of the upwelling, suppressing it, blocking the cold, nutrient-rich water from reaching the surface. The ocean warms, the food chain collapses, the atmosphere above the warm water changes. Rain patterns that have followed the same path for thousands of years shift. Suddenly, it is flooding in places that should be dry, and drought in places that should be wet. That is the mechanism. Simple in theory, catastrophic in practice. But what is happening right now is not the standard version of this mechanism. What is happening right now is something scientists are describing as potentially outside the range of what their models were built to handle. And to understand why, you need to understand what happened the last time that sentence was true, not 1997. Before that, much further back, In January 1878, the oceanic Niño index, the number scientists use to measure El Niño intensity, crossed plus 3.0 degrees Celsius. That is the only time in the entire instrumental record that it has ever reached that level. The event that produced it began in 1876 and lasted nearly 3 years. It did not produce a weather disaster. It produced a civilizational one. From 1876 to 1878, simultaneous droughts struck India, China, Brazil, and large parts of Africa. The monsoon failed in South Asia for 2 consecutive years. The Yangtze River basin dried out. Crops failed across multiple continents at the same time, not sequentially, not in isolated regions, but simultaneously, because the same atmospheric disruption was operating globally at once. The death toll from what historians now call the global famine of 1876 to 78 is estimated at between 30 and 60 million people. That is approximately 3 to 4% of the entire human population at the time. No single environmental disaster before or since has killed a larger fraction of the people alive when it occurred. Some models for the current event are projecting an ONI above plus 3.0 degrees. That is what is developing in the Pacific right now. To understand what makes this El Niño different, you need to understand how scientists measure it. The primary index they use is called the Oceanic Niño Index, the ONI. It measures the average sea surface temperature in a specific region of the Central Pacific, called the Niño 3.4 region, and compares it to the long-term historical average. A deviation of plus 0.5 degrees Celsius sustained for 5 consecutive 3-month periods qualifies as an El Niño. That is the baseline. That is the threshold where scientists start paying attention. A strong El Niño is classified at plus 1.5 degrees or above. The 1997 to 98 event, the worst on record in the modern era, peaked at around plus 2.3 degrees. As of mid-May 2026, the weekly ONI index in the Niño 3.4 region had already reached plus 0.9 degrees Celsius and was climbing rapidly. The International Research Institute for Climate and Society reported that subsurface temperatures between 150 degrees west and 80 degrees west at depths of 50 to 150 meters had locally reached anomalies of up to 6 degrees above normal. The Southern Oscillation Index, the atmospheric counterpart to the ocean measurement, fell to minus 11.2 in April 2026. That is a strongly negative reading. It means the atmosphere is already responding to the warming ocean. The coupling between ocean and atmosphere that defines a mature El Niño event is already beginning to establish itself. This is unusual. At this stage of development, late May, the 1997 event was not yet showing this level of atmospheric response. The current event is developing faster. NOAA's latest forecast, issued in May 2026, puts the probability of El Niño emerging between June and August at 82%. The European Centre for Medium-Range Weather Forecasts and the Australian Bureau of Meteorology are showing similar numbers. And the ensemble model outputs, the range of possible outcomes that climate centers use to bound their forecasts, are pointing toward something that sits in a category that has only been approached twice in the modern instrumental record. A super El Niño. Defined not just by magnitude, anomalies above plus 2.0 degrees, but by the global disruption it produces. And some of those models are showing anomalies that could exceed plus 3.0 degrees before the event peaks. Let that number sit for a moment. Plus 3.0 degrees above the already elevated modern baseline. The only time the Oni has reached that level in the entire recorded history of this measurement was January 1878. But that surface number is not what is alarming the researchers who track this most closely. What is alarming them is what is sitting below the surface. At roughly 100 meters of depth in the central and eastern Pacific, there is an enormous body of water. Oceanographers call it a Kelvin wave, a slow-moving pulse of thermal energy traveling along the equator, with temperatures running 5 to 6 degrees Celsius above the historical average for that depth. According to the latest data analyzed against NOAA subsurface ocean measurements, that anomaly has in some locations reached nearly 8 degrees above normal. 8 degrees. Not at the surface, underneath it. Waiting. This thermal reservoir extends over a horizontal span stretching from roughly 150 degrees west to 80 degrees west. That is more than 7,000 kilometers of ocean, at depths between 50 and 250 meters. It is not a localized warm patch. It is a continent of heat submerged just below the surface of the world's largest ocean. And it is moving upward. The question is not whether it will affect the surface. It is already affecting the surface. The question is, how much of it reaches the surface, how fast, and whether the atmospheric conditions above the ocean amplify or suppress what happens next. Here is the problem with answering that question. The same weakening of the trade winds that allows El Niño to develop is also the mechanism that pulls that subsurface heat upward. The winds and the ocean heat are in a feedback loop. Weaker winds allow more heat to surface. More heat at the surface further weakens the winds, which allows more heat to surface. This is called a positive feedback loop. And in the history of El Niño monitoring, the last time scientists watched a feedback loop of this magnitude develop in the Pacific was 1997. That should be enough to be alarming on its own. But that is not even the most disturbing part of what the data is showing. The most disturbing part is what happened to the baseline. Over the past 2 decades, the global ocean has absorbed approximately 90% of the excess heat generated by greenhouse gas emissions. The Pacific Ocean in particular has been warming. Not dramatically year over year, but steadily, measurably in every data set. The average that El Niño anomalies are measured against is itself already warmer than it was in 1997. What this means in practical terms is that when you add an El Niño anomaly of plus 2.0 degrees to an ocean baseline that is already 0.5 to 1 degree warmer than it was when the 1997 event hit, you are not dealing with the same phenomenon. You are dealing with a system that has been shifted into a higher energy state and is now being further pushed by the El Niño mechanism on top of that already elevated baseline. Scientists call this stacking. And stacking is one of the reasons that 2023 and 2024, which both saw El Niño conditions, produced global average temperatures that broke records by margins that surprised even the researchers who predicted them. But what is forming now is not the moderate El Niño of 2023. The subsurface heat content in the Pacific right now is substantially higher than it was at the equivalent point in the development of the 2023 event. The speed of development is faster. The atmospheric coupling is establishing earlier. And critically, the baseline on top of which all of this is operating is itself at a record level. There is a concept in physics called path dependence. It means that where a system ends up is not just a function of what forces act on it now, but of the entire history of forces that acted on it before. The Pacific Ocean right now is not a clean slate on which a new El Niño is being written. It is a system that carries the thermal history of 150 years of industrialization, 70 years of rapidly accelerating emissions, and a baseline temperature that is measurably outside the range of any data used to build the forecasting models that governments, insurance companies, and agricultural systems rely on. When climate scientists say the models are pointing at numbers they have never seen before, this is what they mean. They are not being dramatic. They are describing a technical reality. The tools they are using to forecast were not designed for conditions like these. Now, here is where the story becomes something more than a measurement problem. Because a super El Niño does not just produce more extreme versions of what a normal El Niño produces. It restructures the global atmospheric circulation in ways that create entirely new patterns that did not exist in the historical record that climate models were trained on. Start with the fish. Because before it is a climate story, it is an ecological one. The fishing industry off the coast of Peru is one of the oldest in the world. The Peruvian anchoveta, a small fish, maybe 15 centimeters long, is the single most commercially harvested fish species on the planet by weight. In a normal year, Peru catches between 5 and 8 million metric tons of it. That fish feeds aquaculture operations in Asia. It goes into livestock feed in Europe. It is in the food chain of things you eat without knowing it. It exists because of the cold upwelling that El Niño suppresses. In 1997 to 98, Peruvian anchovy catches collapsed by roughly 50%. The marine ecosystem from Ecuador to Chile was devastated. Sea lion populations dropped. Penguin colonies failed to breed. The food chain from microorganism to apex predator simply stopped functioning because the cold, nutrient-rich water had been replaced by warm, nutrient-poor water that nothing could live on. That took years to recover. If the current event reaches the magnitude that the models are projecting, the suppression of upwelling will be more complete and will last longer. The ecosystem that collapsed in 1997 never fully recovered to pre-event levels. Another event of equal or greater magnitude, stacked on top of an ocean that is already warmer, hits a system that is already stressed. But the ocean is only the beginning. Because what happens in the Pacific doesn't stay in the Pacific. A massive area of anomalously warm ocean surface is an enormous energy source. It heats the air above it. That warm, moist air rises and has to go somewhere. Where it goes determines rainfall patterns across entire continents. During a strong El Niño, the band of intense tropical rainfall that normally sits over Indonesia and Australia, called the Intertropical Convergence Zone, shifts east toward the central and eastern Pacific. The result is that Australia dries out, the Amazon dries out, and the western coast of South America, which is normally desert, gets deluged. In the 1997-98 event, parts of coastal Peru received over 3 meters of rainfall in a single season. Regions that averaged less than 50 millimeters per year received thousands. Infrastructure built for desert conditions was submerged. Landslides destroyed roads and villages that had stood for generations. The damage in Peru alone exceeded $3 billion in 1997 dollars. Meanwhile, Indonesia, Australia, and the southern African region experienced drought conditions severe enough to trigger massive wildfires. The Indonesian fires of 1997 to 98, driven by drought conditions created by El Niño, burned approximately 9.7 million hectares and produced a smoke cloud that blanketed Southeast Asia for months, causing respiratory illness across a region of several hundred million people. The health and economic cost was estimated at over $9 billion. That is what a 2.3-degree anomaly produced in 1997. Now consider what the current models are projecting for the food system specifically, because this is where El Niño stops being a weather story and becomes an economic one, and the two are much harder to separate than most coverage suggests. The United Nations World Food Programme published analysis in early 2026, warning that the number of food-insecure people globally could reach levels not seen since the early months of Russia's invasion of Ukraine. When analysts factored in the projected agricultural impacts of a super El Niño, reduced maize, rice, and wheat production in Asia and Australia driven by drought, combined with disrupted monsoon seasons across South Asia, the picture became considerably worse. El Niño events historically put upward price pressure on specific commodities: rice, sugar, cocoa, palm oil. These are not exotic goods. They are inputs into the food systems of countries with populations measured in the hundreds of millions. When those prices rise simultaneously, not because of supply chain disruption or conflict, but because of simultaneous crop failures across multiple continents caused by a single atmospheric event, the shock to food security is not linear. It compounds. Here is what makes the current situation different from every previous El Niño that has been studied. And this is the part that is genuinely new, not in the sense of we should be worried, but in the sense of the science does not yet have a confident answer. The models that climate scientists use to forecast El Niño were built using historical data. They were trained on every El Niño event in the instrumental record going back to roughly 1950. They account for the known variability of the Pacific, the seasonal patterns, the atmospheric teleconnections, all of it. They are sophisticated, well-tested tools. But they were not trained on an ocean that is as warm as the ocean is right now. The background temperature of the Pacific in 2025 and 2026 is outside the range of the data that the models were built on. When scientists run their forecasts and the model outputs show anomalies of plus 2.5 or plus 3.0 degrees, they are working in what they call uncharted territory, not dramatically, not as a rhetorical flourish, but as a literal technical description. The models are extrapolating beyond their training data. In May 2026, sea surface temperatures in parts of the eastern equatorial Pacific were already approaching 29 degrees Celsius. That is not at the critical threshold yet, but it is closer to it at this stage of El Niño development than any event in the modern record has been. And the subsurface heat, that continent-sized mass of up to 8-degree anomaly water sitting between 50 and 250 meters of depth, has not fully reached the surface yet. There is one more element to this that the standard forecast coverage rarely addresses, and it is the one that connects the current event directly to the catastrophe of 1876 to 78. in a way that should change how you think about what is being projected. The global famine of 1876 to 78 was not caused by El Niño alone. Climate researchers at Columbia University's Lamont Doherty Earth Observatory, publishing in the Journal of Climate in 2018, found that the event was caused by an extraordinary combination of 3 simultaneous ocean anomalies: a record-breaking El Niño in the Pacific, a record-strength Indian Ocean dipole, and record warm temperatures in the North Atlantic. All 3 operating at the same time, reinforcing and amplifying each other across different ocean basins. That combination drove simultaneous droughts across Asia, Africa, Brazil, and parts of the Americas, not because of a single forcing, but because of constructive interference between multiple climate systems all pushed to their extremes at once. As of May 2026, the Indian Ocean Dipole Index is also showing anomalous behavior. North Atlantic sea surface temperatures remain at elevated levels. The 3 ocean systems that converged to produce the worst climate disaster in human history per capita are all, simultaneously, showing anomalous readings. That does not mean 1876 to 78 is about to repeat. Modern infrastructure, global food trade, and early warning systems make a repeat of that death toll essentially impossible in the developed world and less likely everywhere else. But it does mean that the atmospheric setup for an event of extraordinary magnitude is not theoretical. It has a historical precedent. And the ocean conditions that produced that precedent are, right now, aligning again. Let's be specific about what the projections say, because this is where the coverage usually gets vague, and the vagueness is the most misleading thing about it. For South America, particularly Peru, Ecuador, and northern Chile, the models are showing a high probability of extreme rainfall events beginning in late 2026 and continuing through the first half of 2027. The coastal infrastructure in these regions was rebuilt after 1997 to 98. But it was rebuilt to handle what 1997 to 98 produced. If the current event exceeds that benchmark, those improvements are not sufficient. Already in early 2026, before El Niño has formally established itself, floods have created crises in Colombia, Peru, and Ecuador, according to the European Commission's Joint Research Center. These are the pre-event conditions. The dry season has not yet arrived. The major El Niño forcing has not yet peaked. For Australia, reduced rainfall across the eastern and southeastern regions is the primary concern. The same drought conditions that preceded the 2019-20 Australian bushfire season, which burned over 18 million hectares and killed or displaced approximately 3 billion animals, were associated with a moderate El Niño-like pattern. A stronger event on top of an already drier landscape creates compounding risk. El Niño-driven drought in Australia also affects the country's wheat and barley production, which feeds global export markets. A significant reduction in Australian grain output does not stay in Australia. It moves through commodity prices into food systems in North Africa, the Middle East, and Southeast Asia. For South and Southeast Asia, the concern is the monsoon. El Niño events historically weaken the South Asian monsoon. The seasonal rainfall that India, Pakistan, Bangladesh, and parts of Southeast Asia depend on for the majority of their annual precipitation and agricultural water. A weaker monsoon in 2026 would reduce rice, wheat, and sugar production across a region that feeds over 2 billion people. The European Union has already flagged that El Niño poses a significant risk to the main agricultural season in parts of Ethiopia, South Sudan, and Sudan, regions already facing acute food insecurity. For North America, the pattern that strong El Niños historically produce is well documented. Wet conditions across California, the Gulf Coast, and the southeastern United States. Increased risk of atmospheric rivers, narrow corridors of intense moisture transport that can drop enormous amounts of rainfall in very short periods. The California floods of 1997 to 98, which caused over $1.1 billion in damage, followed exactly this pattern. The northern United States, Canada, and the Pacific Northwest, by contrast, typically see warmer and drier than normal conditions, which increases wildfire risk and reduces snowpack in the mountain ranges that feed the rivers those regions depend on through the summer. And then there is the global temperature record. When El Niño events peak, they release enormous amounts of heat stored in the ocean into the atmosphere. NOAA has already assessed that 2026 is very likely to be one of the 5 warmest years ever recorded. And that assessment was made before El Niño has even formally established itself. The projections for a super El Niño peaking in late 2026 or early 2027, stacked on top of a baseline already elevated by background warming, point towards something that researchers are beginning to describe in terms that would have seemed extraordinary 5 years ago. Some are already discussing the possibility that 2027 could be the first year in recorded history where the global average temperature anomaly approaches 1.8 degrees Celsius above the pre-industrial baseline. And the models, the same models that correctly forecast the 1997 event, the 2015 event, and every major El Niño in between, are pointing at numbers they have never pointed at before. That is what is happening in the Pacific Ocean right now.